Hello, everyone. Welcome. Welcome to this session on learning mathematics through concepts and examples. Today's topic is inverse function. Let's get started. First of all, let's look at the learning goals for today. So by the end of this session, you should be able to determine whether a given pair of functions are inverse of each other or not. So when two functions are given to you, you are going to check whether they are inverse of each other or not. Second, determine the inverse of a given function. So you're going to learn the procedure on how to determine the inverse of the function. Third one, you'll be able to understand the composition of function with its inverse. So what happened when we take the composition of function with the inverse of that function? And finally, understand the graphical property of the function in relation to its inverse. So if we graph the function and its inverse on the same graphing grid, what happened? We are going to look at that. So those are the big goals for the today. So let's get started with the first example. So in this one, we are asked to prove that the function f of x equal to negative 3x plus 1 and g of x equal to negative 1/3 x minus 1, quantity x minus 1, are inverse of each other. So two functions are given. So we'll start with the given functions. So here, f of x is equal to negative 3 times x plus 1. Make sure you understand the meaning of that. So in this function f, when the input is x, the output will be negative 3 times that input plus 1. So whatever we input, right, in that function machine, your output will be multiplied by negative 3, then added 1. And the next function is g of x, which is equal to, so they have given negative 1/3, the quantity x minus 1. So we are going to distribute that 1/3 and write it like this, negative 1/3 times x, negative 1/3 x, and then plus 1/3. Okay, if we distribute that, negative 1/3 x, if we multiply here, that will be plus 1/3. So that is the function g of x. Now what we're going to do is, there is a trick in, proving that these two functions are inverse of each other. We are going to take the composition of these two functions. Okay, so now let's find the first composition. f o g of x. f o g of x, meaning of that is, inside the function f, you are plugging in function gx. So that is same as f of, then write down the value of g of x. G of x is this one, negative 1/3 x, negative 1/3 x plus 1/3. And then the value of this function f is negative 3 times the value from the domain plus 1. So that will be, for this one, it will be negative 3 times, in place of x, we have negative 1/3 x plus 1/3. Okay, that is negative 3 times x. Then we have a plus 1. Plus 1. So let's simplify that and see what we get. So if we distribute that negative 3, so negative 3 times negative 1/3 is positive 1 times x. That's a positive x. And then if I multiply here, negative 3 times positive 1/3, that will be negative 1. And outside the parenthesis, we have a plus 1. So that is equal to x. So FOG of x is equal to x. That means this composition of f with g of x is an identity function, meaning whatever the input is, you are getting the same output. Similarly, let's find GOF of x. GOF of x. Let's find this composition. This is g of f of x is the inside function, and f of x is negative 3x plus 1. Negative 3x plus 1. So now, in order to simplify this one, we have to use the function rule for g. And g is negative 1/3 x. So I can write negative 1/3. This one, negative 1/3. Then we have x. But in place of x, I have negative 3x plus 1. That is a negative 3x plus 1. And then we have plus negative 1/3 x plus 1/3. Now let's see what we get. If we distribute this 1/3, negative and negative will be positive. 1/3 of 3 is a 1. So 1 times x is a x. And then if I distribute here, that becomes negative 1/3. Outside the parenthesis, we have positive 1/3. And you see that that's equal to x again. So that means this composition is also equal to x. So what we got is, let me write. So what we got is FOG of x is equal to GOF of x. And these are both equal to x. Remember, if the composition of function and the other function in any direction, that is FOG or GOF, is an identity function, meaning of that is this is true if and only if f and g, this is true if and only if f and g are inverses of each other. Okay, this is true if and only if f and g are inverses of each other. So yes, we proved that the function f and g are inverse of each other because we saw that their composition is an identity function. So important note for you, note that the composition of function, okay, composition of function and its inverse is an identity function, is an identity function. Okay, if you take the composition of function and its inverse, that's going to be the identity function. That's an important note for you to remember. In this one, we use that property to prove that f of x and g of x are inverse of each other, because when you try to find their composition, f of g of x and g of f of x, both are identity function. Whatever their input is, we have the same output, meaning that's an identity function. So f of x, f of g of x and g of f of x both are equal to x, and that is true if and only if f and g are inverse of each other. So when we get that, we concluded that the functions are inverse of each other. Okay, that's our first example. Let's see what we have in the next example. So in this next example, they have given a function f of x equal to half x minus 4, and we are asked to answer these two questions. In first part, we are asked to find the inverse function. Okay, in the first part, we are asked to find the inverse function. So in order to find the inverse function, we start with the given function f of x equal to half x minus 4. And you can see that this function, okay, this function f of x equal to half x minus 4, or which is same as y equal to half x minus 4. This is a linear function, so this is one-to-one function. So if the function is one-to-one function, we can find the inverse. So we can say, since f of x is a linear function, okay, since f of x is a linear function, it is one-to-one. So inverse exists. So inverse exists, meaning we can find the inverse. So to find the inverse, what we do is we interchange the role of x and y, because if it is one-to-one function, then we can define a function from the range to the domain, and that is the inverse function. So what we do is we interchange x and y. So let's write that down. Interchanging x and y, what we get is, here we have half x minus 4. So that will be half y minus 4 equal to, we have a y, now that becomes x. Because to find the inverse, we interchange the role of the domain and the range. Because if the function is one-to-one and a new function is defined from the range to the domain, then that function is the inverse function. Okay, now we are going to solve this equation and find the value of y. So if we add 4 on both sides, it will be equal to half y is equal to x plus 4. Now, if we multiply on both sides by 2, we get y equal to 2x plus 8. And this new value of y that we get here, that's our inverse function. So we can write f inverse x is equal to 2x plus 8. Okay, f inverse x is equal to 2x plus 8. That is the inverse of the function. So that is the first part. We did the first part. Remember, we are asked to find the inverse of the function. So in order to find the inverse of the function, your function must be one-to-one function. And this function, half x minus 4, is a linear function, a straight line function. So that's definitely a one-to-one function. Because if you try to draw the horizontal line, it crosses the function or the graph of the function at only one point. So it's one-to-one function. So since the function is one-to-one, inverse exists. And in order to find the inverse, we have to interchange the role of domain and range. That we interchange x and y and then solve for y. And that new y value that you obtain, that is the inverse function. Now for part B, let's see. In part B, we are asked to find f of f inverse -3. And you can clearly see that this is the composition of function with the inverse. And we know that the composition of function with the inverse is an identity function. So we can say this is the composition. Okay, this is the composition of function. This is the composition of function with its inverse. With its inverse. So it is an identity function. So it is an identity function. Meaning of that is, whatever the domain or whatever the input is, it will give you the same output. So this implies the composition of function with the inverse at -3 is equal to -3. Because the input value is -3, output is also negative. It's an identity function. It's not going to lose its identity, right? Whatever is there in the domain, you'll get the same value in the range. And we use this property from our first example, because in the first example, we know that the composition of function and its inverse is an identity function. So that's what we did. So we use the property from first example here. And the second thing we did here is we learned how to find the inverse of the function. Here, the function was the linear function, but the process is same for any function. It can be linear function, it can be quadratic function, restricted quadratic function, I should say, because if we restrict the domain of the quadratic function to certain interval, then we'll be able to find its inverse. But this one, we don't need to restrict the domain because it is always one-to-one function. But the quadratic function may not be one-to-one all the time. So there requires some domain restriction there. Okay, that's our second example. Here is the next example, or I can say this is the last example for this video. Okay. Example, sketch the graph of the function f of x equal to 2x plus 3 and its inverse on the same coordinate axis. Okay, so first of all, let's think of this function f of x equal to, okay, let me do that. F of x equal to 2x plus 3. Because this is a linear function, as you can see, okay, it is y equal to mx plus b. So the slope is 2 and the y-intercept is 3. So for this function, slope, which is rise over run, is equal to 2. 2 means 2 over 1. Meaning of that is you'll go 2 units up. Okay, you'll go 2 units up. That's your rise, 2, and then the run is 1. 2 units up, and then 1 unit to the right. That is the meaning of that. Okay, and then the y-intercept is 0, 3. Y-intercept is 0, 3. That's a 3 there, so 0, 3. That means you can start at 0, 3. So 0, comma 3 is a here. That's a point over there. Let me use the red dot there. Okay, there we go. That's a 0, comma 3. And then we know that because the slope is 2, we go 2 units up and 1 unit to the right. So 2 units up and 1 unit to the right is this one. You can follow the same process and get few more points. 2 units up and 1 unit to the right. You are there. So you can get a couple of points like that. 2 unit up and 1 unit to the right. Like that. You can get a couple of points using that process. And once you do that, you can connect this dot. Okay. You can connect these dots to draw the line or draw the function. So that is our graph. Okay, that is the graph of the function. Okay, that is the graph of the function. So you can look at these points. You can analyze these points and see what you'll get. So the first point here, this one is 0, comma 3. Let me write those points. 0, comma 3. Next point here is 1, comma 5. Okay, 1, comma 5. And then the next point, you can see it is 2, comma 7. 2, comma 7. And then the next one is 3, comma 9. 3, comma 9. So we got those points 0, 3, 1, 5, 2, 7, 3, 9. And what we know from the previous example here is for the function and the inverse, the domain and range values are interchanged. So if we want to graph the inverse of this function, we have to interchange the point and plot. That means in place of 0, comma 3, it will be 3, comma 0. Okay, it will be 3, comma 0, x3, y0. So 3, comma 0 is there. That is 3, comma 0. 3, comma 0. Let me also put the red dot there for that. Okay, 3, comma 0. Next one is 1, comma 5. And if we change the domain and range, it will be 5, comma 1. So 5, comma 1 will be here. You can see 5, comma 1. Next one will be 7, comma 2. Here is 2, comma 7. So it will be 7, comma 2. 7, comma 2 is there. And then the next one we have is 3, comma 9. If we change the domain and range, it will be 9, comma 3. Okay, it will be 9, comma 3 over there. So now if we try to sketch the graph, hold 9, comma 1, I'm going to remove this last dot for a minute because just those 3 dots will give enough information. That one is 9, comma 3. So 9 is here. 3 will be a little bit up there. So we can do that. One thing to note here, we were going 2 up and then, 2 up and 1 horizontally. Here we are going 2 horizontally and 1 up. 2 horizontally, 1 up. So we can do 2 horizontally and 1 up. So that last point will be, okay, 2 horizontally and 1 up. It will be somewhere there. That is your 9, comma 3. Now we can join these dots and draw the line. So let's try to draw the line properly. Okay. Let me fix the line properly. It's not super cool there. Okay. I think that looks fantastic. Okay, 0, 3. I'm going to skip 1 point and write the other one. Then this will be 2, comma 7 and so on. Okay. This is the graph of that inverse function. I didn't find the inverse. If you try to find the inverse, let's see what will be the inverse. You can see to find the inverse, we have y equal to 2x plus 3. To find inverse, we interchange we interchange x and y. That's what we know from the previous example. And we can do that because this is a one-to-one function. It's a linear function. So it becomes 2y plus 3, 2y plus 3 equal to x. Because for 2x plus 3, we write 2y plus 3. And for this y, we write x. Now we subtract 3 on both sides. So it becomes 2y equal to x minus 3. And we divide throughout by 2. So we get y equal to, if we divide by 2, that's half x. If we divide by 2, 3 over 2. So that means the inverse function, okay, inverse function is half x minus 3 over 2. Half x minus 3 over 2. So the slope is 1 over 2. That means we have a rise of 1 and run 2. You can check at any point you want. So here you can see rise 1, run 2. Rise 1, run 2. Rise 1, run 2. Okay, so that is the slope. I mean, yeah, that's the slope. And then y-intercept, you can see it is negative 3 over 2 or negative 1.5. So this is 1, down here is 2. This line is going from the middle. So that's why that is 1.5. Okay, so let me just show you very clearly. So it's just like that. 1.5 will be in the middle like that. Right? That's 1.5. Okay, so we draw the graph even without finding the actual inverse. Now the question here is, we are not just asked to draw the graph of the function and the inverse, but the question is, using the graph, you are looking at the graph, okay? Using the graph, state what you notice. When you look at this graph, what do you notice? That's what you're going to explain. So that is the main thing here. So now, if I think of a line, see, if I draw a line like this, okay, if I draw a line like this line here, the dashed line, you can see that this line passes through 1, 1, 2, 2. If you look at the points on that line, see, it's a 1, 1, x and y are equal, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10. Same thing on this side, negative 1, negative 1, negative 2, negative 2. That means this one is the line y equal to x. Okay, that is the line y equal to x. Now, if you try to analyze one point, you don't need to analyze all, but just look at one point there. For example, if we take this point on the line, you can see that, hold on, let's do it a little bit different, not that point. If I take this point, let's say 1, 5. If I take 1, 5 and try to reflect that point about this line, about the red line, you will get this point over here, which is 5, 1. Okay, that is a 5, 1. So when you take a point on the original function and try to reflect it about the line y equal to x, you get the point on the inverse function. Okay, point from the original function. If you reflect about the line y equal to x, you get the point on the inverse, on the graph of the inverse function. Same thing here, this one 0, 3. If we reflect about the line, you can see that you get that new point, which is 3, 0. All the points, in fact, all the points on the original function is when they are reflected about the line y equal to x, we get the point on the inverse function. When you reflect 2, 7 about the line, we get 7, 2. Okay, 2, 7 reflected here. This is 7, 2. Let me write that correctly, 7, 2. Similarly, if you reflect this 3, 9, you'll get this point here, which is 9, 3. That is a 9, 3. So that means when the points on the graph of f of x are reflected about the line y equal to x, we get the points on the graph of the inverse function. Meaning of that is this line, okay, graph of f of x, when the graph of f of x is reflected about the line y equal to x, we get the graph of the inverse. So that's what we notice. So let's write that down. when the graph of y equal to f of x is reflected about the line y equal to x. Okay, if the graph of y equal to f of x is reflected about the line, if the graph of y equal to f of x is reflected about the line y equal to x, we get the graph of y equal to f inverse x. We get the graph of y equal to f inverse x. That means the graph of y equal to f of x, okay, the graph of y equal to f of x, this original line, y equal to f of x, and the graph of the inverse, y equal to f inverse x. They are, okay, graph of y equal to f of x and graph of y equal to f inverse x. They are the actual reflection about the line y equal to x. This line is y equal to x because every point on the line has the same x and y coordinate. And this shows that y and x are equal here. And that's true because when we think of the graph of the function and the inverse, we obtain it by changing the x and y. So we are treating them equal, but we are flipping them around. Okay, so that's how we can work on different problems on inverse of a function. So I hope you enjoyed this video. I hope you are able to learn something. Thank you so much for watching, and I'll see you in next video. Till then, have a good day. Bye.